Please subscribe to support the channel. The idea of something reaching or exceeding the speed of light near Earth isn't just thrilling, it's terrifying. The speed of light, about 299,792 kilometers per second, is nature's ultimate speed limit, the boundary that nothing with mass can cross. But if, somehow, something did, whether a spacecraft, a particle, or an unknown force, the consequences would be beyond catastrophic. The immense buildup of energy would distort spacetime itself, and the resulting release could vaporize the atmosphere, crack the planet's crust, and erase Earth in an instant. This isn't just a story about speed. It's about the fragile balance that keeps our world safe, and what happens if something dares to break it. According to Einstein's theory of relativity, the speed of light isn't just fast, it's the fundamental ceiling of motion in the universe. As an object with mass accelerates closer to that limit, its relativistic mass increases, meaning it effectively becomes heavier. The faster it moves, the more energy is required to push it faster still. Eventually, the energy needed becomes infinite. And since infinity can't be reached by any means, chemical, nuclear, or even theoretical antimatter drives, nothing with mass can ever actually hit light speed. Photons can do it because they have no rest mass. They were born traveling at light speed. But for anything else, a spaceship, a grain of dust, even a single proton, the math simply refuses to allow it. Yet if we stretch the imagination and break the rules of physics for a moment, what would that really mean? Suppose, by some miracle or alien technology, a mass-bearing object did reach light speed near Earth. The laws of time and energy would collapse in its wake. From the object's perspective, time would freeze, seconds stretching into eternities, while from our perspective, it would unleash a surge of energy so intense that it could unravel atoms themselves. The boundaries between space, time, and matter would blur, and the vacuum around it might boil with quantum chaos. In this scenario, light-speed travel wouldn't be transportation. It would be transformation, an event where the universe itself struggles to define what just happened. And that brings us to the next stage, the terrifying buildup of energy that occurs as an object approaches that forbidden limit, a force so immense it could tear the planet apart long before light speed is ever reached. As an object pushes closer and closer to the speed of light, something extraordinary happens. Its energy doesn't just rise gradually, it skyrockets beyond comprehension. The universe begins to resist its motion, as though reality itself is pushing back. Every bit of acceleration demands exponentially more energy, until even the tiniest increase in speed requires an amount of power greater than entire stars can produce. A small spacecraft, no larger than a car, moving at a fraction below light speed would hold enough kinetic energy to outshine the sun for entire moments. That's not poetic exaggeration, it's the raw truth of how the universe handles speed. To put this into perspective, imagine a single pebble traveling at that velocity. The energy locked within it would make the largest nuclear bomb humanity has ever created seem like a spark from a matchstick. The faster it goes, the more destructive it becomes, not linearly, but explosively, exponentially. Each fraction of light speed reached is another order of magnitude of devastation stored inside. By the time an object nears that ultimate limit, it's carrying so much energy that even the act of existing becomes dangerous. The space around it would tremble with radiation. Particles torn from its surface would blaze like miniature suns. The very vacuum might ripple, as though space itself were under stress. And if such an object ever approached Earth, its mere presence would mean impending catastrophe. The energy concentrated in its motion wouldn't need to be released deliberately. Contact with a single molecule of air would be enough to unleash destruction greater than any weapon conceived. That is the horrifying beauty of light-speed motion. It transforms even the smallest speck of matter into something capable of ending worlds. And this unimaginable force leads naturally to a chilling comparison. How does this energy measure up to the greatest destructive events we already know of? What happens when the power of near light-speed motion is compared to nuclear blasts, asteroid impacts, and the radiant fury of the sun itself? When we begin to compare the energy of an object approaching light speed to the most violent forces known to humankind, the scale becomes almost impossible to grasp. It's one thing to speak of nuclear bombs or asteroid strikes, but those are small ripples compared to the oceanic violence that relativistic energy would unleash. The largest nuclear device ever detonated by humans, the Tsar Bomba, released a fireball that stretched tens of kilometers wide and generated shockwaves that circled the Earth 3 times. That blast carried roughly 50 megatons of TNT in energy, enough to destroy a city and devastate everything for hundreds of miles. Yet, if you were to compare that explosion to the energy held in even a small pebble moving at a significant fraction of light speed, the difference would be staggering. The relativistic pebble would contain billions of times more energy than the Tsar Bomba. Not hundreds, not thousands, but billions. It would be as if every nuclear weapon ever built detonated in the same instant. But yet, even that still underestimates the scale. Now consider asteroid impacts, the kind that have shaped the face of our planet and ended entire eras of life. The Chicxulub impact, which wiped out the dinosaurs about 66 million years ago, delivered energy equivalent to roughly 100 trillion tons of TNT. That's an explosion so massive that it threw debris around the world, set the atmosphere on fire, and plunged Earth into years of darkness. But even that impact pales beside the energy of an object approaching the speed of light. A spacecraft no larger than a refrigerator, moving close to that ultimate limit, would strike with millions of times more energy than the dinosaur-killing asteroid. In fact, such an impact wouldn't just cause extinction, it would cause obliteration. The Earth itself could disintegrate under that release of power, reduced to a cloud of incandescent debris spreading out into the void. And yet, those examples are still grounded in the realm of familiar destruction. Nuclear fire and asteroid impacts are things we can visualize. We can imagine explosions, shockwaves, craters. But the kinetic energy of something nearing light speed moves far beyond our imagination's comfort zone. It enters the territory of cosmic phenomena, of supernovae, quasars, and gamma-ray bursts. A near-light-speed object could unleash more energy in a single instant than our sun emits over millennia. To give a sense of scale, the sun releases an amount of energy every second that would vaporize every ocean on Earth and melt the crust into lava. And yet, over time, that steady output is gentle enough to sustain life. The relativistic energy of a fast-moving craft would release that same power all at once, condensed into a moment so brief that the human brain could never perceive it. It would be as though a piece of a star were slammed directly into the planet, turning everything within sight, rock, air, and ocean, into plasma hotter than the core of the sun itself. At that level of energy, explosion no longer feels like the right word. It's more accurate to think of it as a total conversion, a transmutation of matter into radiant fury. Every atom in the object and in the matter it encounters would be torn apart, their constituent particles annihilating into bursts of pure energy. The surrounding air would ignite instantly, not in flames, but in a blinding flood of gamma radiation. The atmosphere would boil away, continents would vaporize, and the shockwave would travel faster than any sound ever could, because at that scale, even the concept of sound loses meaning. There would be no air left to carry it. And here's where the mind truly falters. That's the effect of just one impact. Even if the object didn't strike Earth directly, even if it merely passed nearby, the radiation, the magnetic field distortions, and the gravitational disturbances caused by its unimaginable energy would be catastrophic. The surrounding space would roar with bursts of radiation powerful enough to sterilize life on the moon and beyond. In every direction, the wave of destruction would extend that word like a cosmic pulse, altering everything it touched. When you compare this to known natural events, it becomes clear that nothing in human experience, not even in recorded cosmic observation, perfectly matches the violence of a mass approaching light speed. Even the most powerful gamma-ray bursts observed by astronomers, which release more energy in seconds than our sun does in its entire lifetime, are thought to come from collapsing stars or merging neutron stars, the most extreme objects in existence. Yet, A light-speed collision near Earth would release a similar magnitude of energy, compressed into an unimaginably small point in time and space, right in our own cosmic neighborhood. It would be as though a supernova had gone off inside our atmosphere. That's why the idea of near light-speed travel isn't just impossible because of energy demands, it's dangerous even to contemplate. The sheer destructive potential would dwarf anything humanity or nature has ever produced. A single experiment gone wrong or a hypothetical technology misused could end not just civilization, but the planet itself. In this sense, the speed of light isn't just the limit set by physics. It's a safety mechanism built into the universe, a natural barrier protecting us from forces we're not meant to unleash. And yet, understanding that scale of energy helps set the stage for what happens next. Because if something ever reached those speeds, it wouldn't just release its energy in one catastrophic explosion. The process of moving at that velocity itself would trigger constant destruction, radiating outward as the object tore through the air, space, and matter around it. Those consequences begin with relativistic shockwaves, invisible but devastating fronts of radiation and energy that ripple through the fabric of existence itself. As an object moves through the cosmos, it always interacts with the space around it, through air, dust, magnetic field, and even the faint traces of gas that drift between the planets. At ordinary speeds, these interactions are gentle, almost invisible. But when an object begins to approach the speed of light, those same interactions turn lethal. Every molecule of air, every straight particle of cosmic dust becomes a bullet of pure energy. And as an object slices through the atmosphere or even through near empty space, it creates what physicists call relativistic shockwaves. Waves of compressed radiation and energy so violent that they defy comparison to anything that has ever occurred naturally near Earth. To imagine this, picture the sonic boom created by a jet breaking the sound barrier. That boom is a release of pressure, a shockwave in air caused by the plane moving faster than the sound can travel through it. Now multiply that idea by an unthinkable number. At near light speed, instead of a pressure wave of sound, you get a radiation wave, a front of compressed photons, particles, and electromagnetic energy moving ahead of the object with unimaginable intensity. The air molecules ahead of it don't simply get pushed aside. They are slammed with such force that their electrons are ripped away, their nuclei shattered, and their atoms fused into plasma hotter than the sun itself. The object would essentially create a corridor of destruction, a tunnel of fire and radiation wherever it passed. If such an event occurred within the Earth's atmosphere, the consequences would be immediate and total. The air in front of the object would not merely heat up, it would vaporize in an instant, creating a chain reaction of energy release that would tear through the atmosphere like a tidal wave of fire. The ground below would not stand a chance. Even before the object itself touched the surface, the shockwave of energy and radiation would hit the planet like an invisible hammer. The flash of light would outshine the sun, and in that instant, anything within thousands of kilometers, cities, oceans, mountains, would be reduced to plasma. But even outside of the atmosphere, in the vacuum of space, these shockwaves would be no less catastrophic. Space isn't truly empty. It's filled with particles, magnetic fields, and interplanetary dust. At near light speed, every microscopic speck the object encounters would erupt into a burst of high-energy radiation, creating a continuous storm of gamma rays that would fan out across space. These bursts would be so intense that they'd fry the electronics on satellites, strip the ozone layer from Earth, and sterilize the planet in moments. In fact, from a distance, it would resemble the most intense cosmic events we've ever detected. A gamma ray burst, those mysterious explosions that astronomers sometimes observe in distant galaxies. The difference is that this one would be happening right next to us. The very space around the moving object would distort from the energy it carries. The electromagnetic fields generated by its motion would bend and twist the surrounding vacuum, and the radiation pressure would build up to levels so extreme that space itself would seem to shimmer and tear. These shockwaves wouldn't just move through matter, they'd move through the fabric of space-time itself, shaking the invisible web of physics that holds everything together. As the object pushed forward, it would compress the light ahead of it into higher and higher energies until even the photons, the building blocks of light, carried enough force to destroy whatever they struck. At the leading edge of the object, there would be no color, no sound, no discernible shape, just a blinding burst of energy, brighter than any sun, traveling with it like a halo of destruction. And behind it, the devastation wouldn't fade. It would linger, as atmospheric gases reignited, as molten rock flowed like liquid metal, and as radiation scoured every surface it touched. The object would essentially be enveloped in a cocoon of death, an expanding bubble of annihilation where matter and energy fused in violent equilibrium.
If we scale this up, the numbers become meaningless. A spacecraft-sized object traveling at a significant fraction of light speed would generate a shockwave powerful enough to boil entire oceans from orbit. The Earth would not merely be burned, it would be unmade. The crust would peel away like the skin of an overexposed planet, and the atmosphere would erupt outward into space, stripped by radiation and force. And yet, even before physical impact, the very act of moving at such velocity through our neighborhood would be enough to devastate it entirely. The relativistic shockwaves would act like a cosmic scythe, slicing through anything in their path, leaving nothing behind but radiation and ruin. And this is just the beginning of what happens when light-speed motion collides with matter. Because for every shockwave generated by motion, there's also an explosion waiting to happen at every point of contact. Every atom the object meets releases incomprehensible energy, and those collisions don't stop, they multiply. That's where the destruction becomes unstoppable, when matter itself becomes the fuel for its own annihilation. At near light speeds, every encounter between matter and motion turns into a cataclysm. The closer an object gets to the speed of light, the more violent each collision becomes, because even the tiniest particle it meets is packed with the energy of entire bombs. A single grain of dust, a lone air molecule, or a drifting atom isn't harmless anymore. It's a trigger, a fuse for an explosion of impossible magnitude. When the moving object slams into that atom, the energy released is so vast that it doesn't just destroy the atom, it disintegrates it completely, converting its mass into radiation. That energy bursts outward, hitting nearby atoms and ripping them apart in turn. One collision becomes 1,000, 1,000 become billions, and the chain reaction spreads faster than thought, faster than the eye can see, faster than life can end. If this object were traveling through Earth's atmosphere, the air itself would become its weapon. Each molecule of nitrogen and oxygen would act like a mini detonator. The first contact would produce a flash of radiation hotter than the core of a star. The next contact would multiply that reaction, feeding on itself until the entire surrounding atmosphere erupted into a continuous stream of plasma. There would be no flames, no smoke, only light and raw energy. The sky would transform into a burning sheet of superheated gas, rolling away from the object like a tidal wave of fire. The temperature would rise so quickly that the oceans below would vaporize before the sound of the impact could even form. Even in the emptiness of space, this chain reaction wouldn't stop. Interplanetary space is full of dust, bits of rock, and stray atoms. A thin mist of matter that, at ordinary speeds, is harmless. But to something moving at a fraction below light speed, that dust becomes a field of bombs waiting to go off. Each particle it collides with would explode into radiation, adding to the already unimaginable energy being released. The object would trail a wake of destruction for millions of kilometers, a glowing scar of ionized gas and shattered particles, blazing like a second sun. In that trail, temperatures would reach levels that no known material could withstand. Even atomic nuclei would be torn apart, leaving nothing but a flood of high-energy particles rushing outward into the void. Now imagine this happening near Earth. Even if the object didn't directly strike the surface, its passage through the upper atmosphere would be enough to end the world. The cascading collisions would ignite the sky itself. Air molecules torn apart at near light speed would unleash bursts of radiation so intense that they'd rip electrons from atoms thousands of kilometers away. The upper layers of the atmosphere would fluoresce with lethal gamma rays, sterilizing the surface in microseconds. Cities would vanish not from explosion or impact, but from the simple fact that matter, the very stuff they're made of, would cease to exist as it's transformed into energy. The line between solid, liquid, and gas would disappear, replaced by a storm of plasma and radiation. The process feeds itself. Each new collision produces more radiation, which in turn triggers more collisions, spreading destruction in every direction. It's a feedback loop of annihilation, growing faster the longer it continues. At a certain point, it no longer matters whether the object keeps moving. The chain reaction alone is enough to unmake everything around it. The air would burn, the seas would boil, and the crust would crack from the sheer thermal stress. The planet would effectively begin to melt from the outside in. And because the energy being released is relativistic, it would radiate outward at nearly the speed of light itself, giving nothing and no one the time to react or escape. And yet, as devastating as this cascading destruction is, it's still only part of the picture. Because the worst comes when the object stops moving freely, when, after tearing through the atmosphere or space, it finally collides with a denser region of matter. The frictionless void ends, and what follows is the most violent release of energy possible in the universe, a detonation beyond comprehension, the vaporization scenario. That's when the stored kinetic energy finally bursts outward, not just destroying everything it touches, but erasing the very concept of solid matter itself. As long as an object traveling near light speed moves through empty space, it experiences a kind of eerie calm. Out there, in the near-perfect vacuum, friction doesn't exist in any meaningful way. There's no resistance, no atmosphere to slow it down, no surface to slam into. Only the occasional ghost-like presence of a dust particle or atom that briefly flares into radiation before vanishing into the void. But this fragile piece is temporary, because the instant that object meets any substantial matter, the thin upper layers of Earth's atmosphere, a drifting asteroid, or even the edge of a planet's magnetic field, that calm ends with absolute violence. The frictionless journey stops, and in that instant, the vaporization scenario begins. The amount of energy stored in an object moving at near light speed is so immense that its impact doesn't just destroy, it erases. The kinetic energy released upon collision would dwarf every source of power humanity has ever harnessed, all detonating in a single impossible flash. Even a small probe, something the size of a smartphone, traveling at that speed would unleash energy comparable to billions of hydrogen bombs exploding at once. To put that into perspective, a single hydrogen bomb can release enough energy to vaporize an entire city and flatten the landscape for miles. Billions of them compressed into one moment wouldn't just destroy continents. They would vaporize the Earth's crust, boil its oceans, and ignite its atmosphere in an instant.
When the object collides with the air, the impact would not create a simple explosion. Instead, it would trigger a transformation. Matter turning directly into energy. The air molecules in front of it would compress so violently that their atomic bonds would break apart, the nuclei themselves torn to pieces. The object's own material would disintegrate at the same time, every atom shredded by the force of its own momentum. The collision would be so intense that it would create temperatures billions of degrees hotter than the sun's core. A brief, blinding moment when Earth's atmosphere would become a roaring inferno of plasma. Everything within thousands of kilometers would cease to exist as solid matter. This eruption of energy would expand outward faster than sound, faster than thought. The explosion's leading edge would be a wall of radiation, gamma rays, X-rays, and searing ultraviolet light, blasting through the air and ground alike. Within milliseconds, the heat would melt rock, vaporize oceans, and turn soil into glass. The Earth's surface around the impact point would effectively become a temporary star, a glowing sphere of superheated matter expanding outward before collapsing into molten chaos. The planet's atmosphere would ignite, glowing white-hot as the shockwave raced around the globe, shaking the crust and boiling away everything alive. But the devastation wouldn't stop at the surface. The energy released would be so concentrated that it would penetrate deep into the planet, sending shockwaves through the mantle and core. Massive seismic waves would travel around the world, cracking the crust open like shattered glass. Lava and vaporized rock would erupt in all directions, and the heat would rise so high that even metals in the planet's core might temporarily liquefy or vaporize. The oceans, if any remained, would flash into steam, expanding violently enough to strip away parts of the atmosphere completely. Even if the object didn't strike directly, even if it simply skimmed through the atmosphere, the result would still be fatal for the planet. The air friction alone would release energy equal to multiple extinction-level impacts. The wake left behind would form a glowing trail across the sky, bright enough to be seen from other planets, its shock waves radiating through the upper atmosphere and into space. The heat would set the world ablaze, while the radiation pouring outward would sterilize everything in its path. The explosion would last only moments, but its consequences would linger for ages. An entire biosphere burned away in seconds. And as the vaporization unfolds, the energy continues to multiply, because every fragment of matter caught in the blast feeds back into the reaction. The expanding plasma cloud collides with more of the atmosphere, adding yet more fuel to the inferno. The boundaries between air, land, and sea blur. They all become part of a single churning storm of radiant energy. In that moment, Earth would no longer be a planet. It would be a luminous fireball, its surface indistinguishable from the chaos of a newborn star. This is the nightmare of the vaporization scenario, where the smooth, frictionless flight of a near light-speed object ends, and the stored power of motion transforms into total planetary annihilation. Yet, as unthinkable as this is, it's only one stage of destruction. The energy released wouldn't just stop at melting rock and burning atmosphere. It would expand outward, reaching into the sky itself. Because once the vaporization begins, the next step is unavoidable: the annihilation of the atmosphere, as the very air that makes life possible becomes the next victim of this impossible speed. The moment the vaporization event begins, the atmosphere, the delicate, life-sustaining veil that protects Earth, becomes the next casualty. It takes billions of years for a planet to build an atmosphere like ours, a thin, balanced layer of gases that nurtures oceans, weather, and breath. But all it would take to erase it is one near-light-speed object. The blast from such an impact would not just tear through the air, it would unmake it. Every molecule of nitrogen, oxygen, and carbon dioxide would be stripped of electrons, shattered into ions and subatomic debris, and hurled outward with catastrophic force. At the epicenter, the collision would instantly convert air into plasma, a state of matter so hot and energized that it behaves more like lightning than gas. This plasma would expand outward, pushing through the rest of the atmosphere in a shock front so intense that it would dwarf even the most powerful volcanic eruptions or meteor impacts. Within seconds, the atmospheric pressure around the globe would collapse. The skies would light up in an unbroken, blinding white glare, as the air itself combusted in a chain reaction of ignition. This wouldn't be fire in any normal sense. There would be no flames licking across the sky, but rather a planet-wide ionization event, a storm of radiation transforming the very medium that carries sound and sustains life into pure energy. Everywhere the blast reached, the atmosphere would be swept away. The force would push upward with such violence that the upper layers of air would be ejected into space. It would be like a reverse explosion. Instead of something striking the ground and throwing debris upward, the energy would surge from the planet outward, blowing the sky itself off the world. The ionized gases would form a glowing halo of material, briefly encircling Earth like a shell of fire before dissipating into the vacuum. What remained of the lower atmosphere would continue to boil, churned by hurricane-force winds and torn apart by the gravitational chaos unleashed by the energy release. The radiation pouring from the impact would compound the destruction. Gamma rays and high-energy particles would strip electrons from every atom they touched, turning the air into a massive conductor. The electromagnetic chaos would cause lightning-like discharges on a global scale, arcing across the sky in flashes of blinding blue and white. But there would be no rain to follow. The heat would have long since vaporized all water, leaving only a haze of superheated vapor rising from what used to be oceans. The upper layers of the atmosphere, pushed beyond their thermal limits, would escape into space entirely, bleeding away in glowing streams that would trail behind the planet like the tail of a dying comet. Within minutes, the blue planet would no longer be blue. From orbit, Earth would appear as a glowing orb of molten rock, its skies gone, its clouds erased. The atmosphere that once scattered sunlight into soft blues and pinks would now exist only as a thin envelope of expanding plasma drifting away from the planet at tens of thousands of kilometers per hour. The oxygen that once fed fires, life and breath would be gone. The nitrogen that moderated temperature and supported ecosystems would be torn apart at the atomic level. The very air, the invisible cradle of all living sound, would be stripped, leaving only silence. The absence of the atmosphere would have profound effects beyond the immediate destruction. With no air to distribute heat, the surface would alternate between extremes: the molten glow of impact zones and the instant freezing of the dark side, where the absence of sunlight would cause the remaining material to crystallize in seconds. Without atmospheric pressure, any remaining water would boil away instantly, and the oceans would erupt in colossal jets of steam that quickly dissipated into the void. Dust and molten debris ejected by the explosion would escape Earth's weakened gravity, forming a debris cloud that might linger in orbit for centuries, a faint, glittering memorial to the planet that once was.
Even if some pockets of atmosphere somehow clung to the shattered remnants of the crust, they would be too toxic and unstable to support anything resembling life. They'd be filled with radioactive isotopes, carbon ash, and vaporized metals, a soup of poison surrounding a dead world. The balance of gases that took eons to evolve would be lost forever. The planet's identity as a habitable world would vanish in moments, replaced by the harsh, airless silence of space. And yet, the destruction wouldn't end there, because the removal of the atmosphere is only one layer of catastrophe. Beneath the surface, the planet itself would still be trembling from the energy unleashed. The immense heat and pressure would begin to warp Earth's gravitational equilibrium, disturbing the very shape of the planet and the way it interacts with the space around it. The energy concentrated in that single event would be so great that it could start to bend gravity itself, pulling oceans, crust, and core in ways nature never intended. The next stage of this unimaginable sequence would no longer be about air or fire. It would be about the gravitational consequences of trying to contain such impossible energy within a fragile world. When so much energy is concentrated into a single object, reality itself begins to bend. Gravity, that quiet, invisible force that shapes everything from falling leaves to the orbits of stars, starts to behave differently. Under normal conditions, gravity is a gentle sculptor. It pulls oceans toward the moon, keeps planets circling the sun, and binds the fabric of the cosmos in elegant order.
But when an object carries near infinite energy by moving close to the speed of light, gravity ceases to be gentle. It becomes distorted, warped, twisted by the sheer density of energy concentrated into one point in space. The result is a local gravitational storm, a curvature of spacetime so extreme that it could tear apart the balance of Earth's natural systems long before any physical impact ever occurs. Even before the object makes contact with the planet, its passage would create gravitational disturbances strong enough to ripple through the atmosphere and oceans. Earth's tides, normally driven by the distant pull of the moon, would surge violently, no longer following predictable cycles, but heaving upward in chaotic bursts. The oceans could swell hundreds of meters higher than normal, not because of wind or weather, but because the planet's gravitational equilibrium would be momentarily thrown out of balance. The crust beneath those oceans would flex and buckle, as if the entire planet were groaning under the stress of an invisible hand reshaping it. As the object approached, the curvature of spacetime around it would intensify. According to relativity, mass and energy are equivalent, and at such extreme velocities, the energy of motion becomes so enormous that it effectively increases the object's gravitational pull. In practical terms, this means that the near-light-speed craft would begin acting like a moving singularity, distorting the space through which it travels. The closer it got to Earth, the more this distortion would affect everything nearby. Satellites would veer off course, the moon's orbit could subtly shift, even the delicate balance of Earth's rotation might wobble as the gravitational field of the object passed through. The ground itself would feel the effects. Crustal plates, already floating atop a molten mantle, would respond to even small fluctuations in gravitational force. As the distortion grew stronger, tectonic stresses would build up rapidly. Fault lines would rupture across continents. Volcanoes might erupt in chain reactions, spewing ash and magma into the chaos above. The planet's magnetic field, tied intimately to its molten core, could become unstable, fluctuating wildly as gravitational strain altered the flow of iron deep within the Earth. For a brief moment, gravity itself would no longer feel consistent. What we think of as down might change slightly, imperceptible to the senses, but catastrophically for the structures of nature and civilization alike. Now imagine the moment of impact. When the object strikes, the energy release doesn't simply blow matter outward, it also compresses space-time at the point of collision. The sheer density of energy could momentarily create gravitational fields thousands of times stronger than normal, strong enough to drag surrounding material inward before hurling it outward in the explosion that follows. The planet would convulse as these opposing forces played out, gravity pulling in, energy blasting out. The result would be waves of gravitational energy radiating from the impact site, spreading through the Earth and outward into space, distorting everything in their path. These waves would act like invisible tsunamis in the fabric of spacetime, rippling through the planet's structure, shaking it to its core. As the Earth's orbit becomes disturbed by this sudden gravitational imbalance, even the relationship between the planet and the sun could begin to shift. A slight alteration in velocity or mass distribution could send Earth spiraling into a new, unstable path, either closer to the sun, where it would be consumed by heat, or farther away, drifting into the frozen dark. If enough mass were vaporized and ejected into space, the change in momentum alone could nudge the planet off its stable course. And as these gravitational ripples propagate outward, they could affect neighboring celestial bodies, tugging subtly on the moon, the planets, even the fragile orbits of satellites circling Mars and Venus. This distortion of gravity wouldn't just be mechanical, it would also be geometrical. Space itself would bend more dramatically near the event, compressing time for anything nearby. If you could somehow observe the moment from a safe distance, which in reality would be impossible, the area around the impact would seem to warp and twist like a lens, light bending unnaturally as it passed through the compressed region of spacetime. The event would resemble a localized gravitational collapse, a phenomenon so extreme that it might even flirt with the creation of a temporary black hole. For those fleeting moments, gravity would cease to follow the familiar rules that hold the planet in harmony. The tides, the crust, the orbit, even the flow of time, all would be thrown into chaos by the sheer weight of motion and energy. It would be as if Earth's delicate gravitational rhythm had been struck like a drum by the universe itself, sending waves of disruption radiating through every layer of existence. But this gravitational upheaval wouldn't happen in isolation. Alongside it, an entirely different form of destruction would ignite, one not driven by motion or mass, but by radiation and magnetism. As the energy of the impact and the movement at near light speed intertwine, they'd generate fields so intense that they'd scorch the planet's surface, fry every circuit, and silence every living heartbeat in an instant. The next wave of destruction would not be gravitational at all, but electromagnetic, a storm of energy that would consume what little remained of a dying world.
The electromagnetic chaos unleashed by a near-light-speed object near Earth would mark the moment when destruction transcends the physical, when the very forces that make life possible turn against it. In ordinary life, electromagnetic energy is gentle and essential. It illuminates the sky, drives our technology, and governs the chemistry that keeps our hearts beating. But when energy is compressed to relativistic levels, those same fields become monstrous, surging, violent, and lethal beyond measure. As the near-light-speed object tears through space, its motion generates magnetic and electric fields of unimaginable intensity, twisting the invisible fabric of electromagnetism into storms that no living thing or piece of technology could ever survive. Even before impact, the mere passage of such an object would trigger a cascade of electromagnetic radiation. The compression of particles and fields ahead of it would produce a burst of gamma rays, the most energetic form of light in existence. These rays would flood outward in every direction, bathing the planet in lethal radiation. Within milliseconds, the atmosphere would glow with ionized energy, as every molecule was stripped of its electrons. For living organisms, this would mean instant death. DNA would be shredded, cells vaporized, and nervous systems fried before a single neuron could fire. The radiation would strike not as heat or pressure, but as pure energetic annihilation, transforming the air itself into a weapon. At the same time, the collision of the object with matter would create magnetic fields far beyond anything naturally found on Earth. Our planet's magnetic field, normally a calm, protective bubble that shields us from cosmic radiation, would be overwhelmed and inverted. The force of the explosion and the relativistic motion would generate magnetic fields trillions of times stronger than Earth's own, comparable to those found near neutron stars. For an instant, the planet would be enveloped in a magnetic storm so intense that it would distort the flow of electrons in every direction. Every circuit, every wire, every atom of metal would become a conduit for destruction. The result would be a planet-wide electromagnetic pulse, or EMP, on a scale beyond imagination. This wouldn't be the kind of pulse that knocks out power grids or disables satellites. This would be a pulse that obliterates them, reducing every piece of technology, from spacecraft to smartphones, into smoldering debris. Satellites in orbit would short out instantly, their circuitry melted by the wave of radiation. Power plants, communication systems, and digital infrastructure on Earth would cease to exist in the same moment. Even if, somehow, any humans were to survive the initial blast, shielded deep underground or within bunkers, the EMP would ensure they'd never communicate, navigate, or rebuild. Every magnetic storage device, every transistor, every power line would be destroyed at the atomic level. The electromagnetic devastation wouldn't stop with technology. It would also interact catastrophically with the physical and biological systems of the planet. The energy surge would generate currents through the ground itself, traveling through the crust and mantle, igniting natural magnetic anomalies and possibly disrupting the flow of molten metal in Earth's core. That, in turn, could distort the geomagnetic field permanently, leaving the planet exposed to cosmic radiation long after the event itself ended. The skies, stripped of protective magnetic shielding, would blaze with auroras, not the gentle ribbons of light seen at the poles, but world-spanning curtains of radiation marking the final breath of the atmosphere as it burned away. For anything alive,
there would be no chance of endurance. The intensity of radiation would reach levels that could tear apart molecular bonds. Even extremophiles, the hardiest forms of life capable of surviving deep in rock or ice, would be cooked by gamma rays that penetrate hundreds of meters underground. The electromagnetic pulse would act like an invisible wave of fire, passing through rock, metal, and flesh alike. In a single instant, every heartbeat, every neuron, every flicker of biological activity would be extinguished. And yet, even as all living systems failed, the devastation would continue rippling outward through the physical ones. The induced magnetic fields and electric currents would pull against the molten metals beneath Earth's crust, creating vast surges of electromagnetic stress that could twist and fracture the planet further. The molten iron in the outer core might begin to flow erratically, driving immense internal pressures and possibly triggering new tectonic ruptures. The planet's own magnetic poles could wander or even reverse. If any fragments of the atmosphere still clung to the planet, they would glow with the last remnants of the radiation storm, turning the Earth into a flickering orb of fading light, surrounded by an expanding cloud of ionized debris. The electromagnetic surge would also extend far into space. The outbursts of radiation and magnetism would travel outward as a relativistic electromagnetic wave, striking the moon, frying its surface with high-energy particles, and bombarding nearby planets with a torrent of deadly radiation. The solar wind, normally a steady stream of charged particles from the sun, would be disrupted, forming chaotic shock fronts that rippled through the solar system. The electromagnetic event near Earth would become a beacon, a blinding flash of high-energy radiation visible across interstellar distances. Any distant observer, perhaps on a world orbiting another star, would see a brief but unmistakable burst of light and gamma rays, announcing that something extraordinary and violent had happened in this corner of the galaxy. And as this storm of radiation fades, what remains is not calm, but chaos. The energy release doesn't stop at radiation or magnetism, it translates into pure mechanical force. The same waves of energy that fry circuits and vaporize cells also shake the very structure of the planet. Mountains crumble, crust fractures, and oceans, if any still exist, boil and erupt. The electromagnetic devastation merges with the mechanical catastrophe, leading to the next stage of annihilation, the continental destruction, when the very bones of the Earth begin to break apart under the weight of the unleashed energy. When that near light-speed object finally releases its full kinetic energy into Earth, the planet itself becomes the battlefield of unimaginable forces. The crust, that thin, fragile shell of rock we call home, would be the first to bear the brunt of the impact. Under normal conditions, the Earth's crust behaves almost rigidly, cracking slowly over millennia as tectonic plates drift and grind. But when confronted with the colossal energy of something moving even a fraction of the speed of light, the crust would not crack gradually, it would shatter, as though the entire planet were made of glass struck by a hammer made of energy. The kinetic energy unleashed would be beyond comprehension. Even a small object, no larger than a pebble, traveling near the speed of light, carries more energy than the largest nuclear arsenal ever conceived. Scaled up to the size of a spacecraft, the amount of power released would be equivalent to billions, perhaps trillions of hydrogen bombs detonating simultaneously. This isn't just an explosion, it's a planetary-scale event capable of transforming solid ground into liquid fire in an instant. At the point of impact, the energy would transfer directly into the crust, generating temperatures hotter than the core of the sun. The rock beneath would not merely melt, it would vaporize. Mountains, continents, and even tectonic plates would lose their integrity as seismic shockwaves tore through the mantle at supersonic speeds. The ground itself would become fluid, a churning sea of molten material radiating outward in all directions. Every volcano on Earth would erupt at once, their fury insignificant compared to the inferno engulfing them. The shock waves would propagate through the entire planetary body, compressing and expanding it in violent pulses that would make the planet ring like a struck bell. As these seismic waves radiated outward, they would meet the oceans, Water, when exposed to that kind of heat and energy, doesn't simply evaporate, it detonates. The seas would flash boil in an instant, expanding to colossal clouds of superheated steam. The immense pressure would launch these vaporized oceans skyward with explosive force, feeding into the already raging inferno above. What was once the tranquil blue surface of the planet would transform into a swirling, boiling chaos of gas and plasma. The vapor would quickly mix with molten debris from the crust, forming a roiling atmosphere of metal vapor and rock dust, a hellish storm encircling what was left of the Earth. Then comes the fragmentation. The crust, weakened by heat and pressure, would begin to fracture globally. Fissures hundreds of kilometers deep would open, connecting the molten mantle to the surface. Rivers of magma would surge upward through these cracks, flooding what remained of the continents. Earthquakes would ripple endlessly, their magnitudes beyond anything measurable, each one capable of leveling entire hemispheres. The distinction between land and sea, between mountain and valley, would vanish. The entire planet would become one continuous landscape of molten destruction, glowing like a miniature sun in the dark void of space. The intense heat would even reach deep into the mantle, destabilizing the planet's internal equilibrium. The boundary between solid and liquid layers would dissolve as the energy tore through every boundary, melting material that had been stable for billions of years. The immense pressure would build up, unable to escape evenly, until the planet began to convulse from within. Sections of crust still intact might buckle and fold under the stress, launching continent-sized slabs of molten rock into the sky. The very concept of ground would lose all meaning. There would be no solid surface left to stand on, only a molten sea churning under a storm of ash and plasma. And yet, even in this unimaginable destruction, the energy wouldn't remain confined to the planet. The explosion's magnitude would be so immense that it would radiate outward, carrying its momentum and fury into the space around Earth. The expanding blast wave of debris, heat, and radiation would push through the void, traveling at a significant fraction of the speed of light. The moon would be the first to feel its wrath, its surface pelted with incandescent debris that could scar it anew, while the shockwave of energy continued onward into the solar system. As the debris escapes, the structure of Earth would begin to unravel further. The molten material still tethered by gravity would briefly attempt to reassemble, but the constant outward motion of the explosion would overpower that cohesion. The gravitational pull that once held continents together would struggle against the inertia of fragments now moving independently. The result would be catastrophic instability. Earth body breaking apart, its form no longer that of a coherent planet, but a field of incandescent fragments slowly spreading into the cold dark. The light from the explosion would outshine the sun for a short while. From millions of kilometers away, Mars and Venus would be bathed in an eerie glow, illuminated by the dying fire of a world's final breath. And as the kinetic energy continued to radiate into the void, it wouldn't stop at the destruction of Earth. The momentum of the expanding energy front would carry the devastation beyond our world, rippling through nearby space and potentially destabilizing the orbits of neighboring planets. That outward surge, the unstoppable cascade of energy and force, would mark the beginning of shockwaves through space, as the destruction of Earth sends violent ripples across the entire solar neighborhood, shaking the delicate balance of celestial mechanics that has held for billions of years.
The destruction of Earth would not end where its surface once stood. The release of energy from a near light-speed impact would send shockwaves rippling outward through the solar system, a wavefront of pure force and radiation expanding across the void. This wouldn't be a simple blast in the traditional sense. There is no air in space to carry sound or pressure as we know it. Instead, the explosion would propagate as an expanding shell of electromagnetic and gravitational energy, a ripple through both matter and space-time itself. The quiet emptiness between worlds would suddenly become the medium for a cosmic roar, felt not as sound but as motion, heat, and disruption. The first victim of this expanding wave would be the moon. Locked in its gentle orbit around Earth for over 4 billion years, the moon would be violently ripped from that balance. The immense kinetic energy release would exert a sudden gravitational recoil,
effectively pushing against the moon's orbit like a sledgehammer. Depending on the angle and distribution of the explosion, the moon could be hurled outward into a higher orbit, flung into interplanetary space, or even torn apart by competing tidal forces. Fragments of Earth, molten, radioactive, and glowing, would slam into its surface, creating a new layer of impact scars over the already ancient craters. For a brief time, the moon would blaze with reflected light from the explosion, a pale companion turned witness to its parent planet's death. But the disturbance would not stop there. The shockwave of energy, though diffused by distance, would continue expanding at tremendous speed. Particles ejected from Earth's disintegration, superheated dust, vaporized rock, and plasma would form a high-velocity front moving outward through the solar system. When this torrent of debris reached Mars, it would pepper the planet's thin atmosphere with a storm of high-energy impacts. Dust and radiation would sweep across its rusty plains, scorching the surface and darkening its skies. Though Mars lies tens of millions of kilometers away, the intensity of the blast could still strip part of its atmosphere and leave new craters across its deserts, a faint echo of Earth's last violet moment. Meanwhile, Venus, shrouded in its dense, reflective clouds, would experience an entirely different fate. The shockwave of radiation, particularly the gamma rays and high-energy particles, would batter its atmosphere, ionizing its upper layers and triggering chain reactions that might alter its chemical balance. The planet's already extreme greenhouse environment could be amplified further, heating it even more intensely. In the aftermath, the solar system's second planet might glow faintly brighter, not because of life or change, but because of the residual energy from a neighbor's annihilation. Further out, the asteroid belt would tremble as the shockwave passed through. Countless fragments of rock and metal would be knocked from their orbits, sent drifting into new trajectories. Some would be flung toward the outer planets, others toward the inner system, a dangerous cascade of debris that could take centuries to settle. The asteroid belt, once a relatively stable region of space, would become a swirling storm of erratic, tumbling remnants. Future collisions among them would create smaller shockwaves, extending the chain of destruction far beyond Earth's immediate vicinity. Even Jupiter and Saturn, massive and distant though they are, could feel subtle gravitational effects from the redistribution of mass and energy. Earth's disappearance, combined with the ejection of vast amounts of material, would slightly alter the solar system's overall balance. Planetary orbits are delicate systems maintained through a precise gravitational dance, and removing or redistributing a planet's mass, especially with explosive force, could shift that equilibrium. The result might be slow, long-term orbital drift, subtle at first, but growing more pronounced over centuries. Closer to home, the inner solar system would become a lethal minefield. Fragments of Earth, some the size of mountains, others reduced to microscopic dust, would hurtle outward at relativistic speeds. These fragments, still carrying staggering kinetic energy, would strike anything in their path with catastrophic force. A single shard of rock from the explosion could obliterate a moon, flatten a planet's surface, or ignite its atmosphere. The solar neighborhood, once serene and orderly, would become a storm of energy and motion, a graveyard of worlds caught in the echo of Earth's demise. Meanwhile, the sun itself would not remain untouched. The incoming radiation and mass ejection from Earth's destruction would slightly alter the solar wind, the constant stream of charged particles flowing outward from the sun. For a short time, the solar system's electromagnetic balance would falter. Solar radiation might flare irregularly as the sun's magnetic field reacts to the influx of charged debris. It's possible that faint ripples in the sun's corona, minor distortions in its outer layer, could appear as the shockwave passes like waves lapping against the edge of a cosmic sea. But the most profound effect of all might be gravitational. The destruction of Earth would create a temporary imbalance in the intricate web of gravitational forces binding the planets together. The missing mass and the dispersal of energy could slightly perturb the orbits of Mercury, Venus, and Mars. Over thousands of years, those small perturbations could accumulate, causing the inner solar system to evolve into new, unstable configurations. Planets might drift closer together, their orbits crossing dangerously, or be nudged further away, changing the very architecture of the solar system. And even beyond our sun's reach, the light and radiation from the event would continue traveling outward. For hundreds of light years, other star systems would register the burst, first as a brilliant flash, then as a faint but enduring pulse of radiation. Astronomers on distant worlds, if they existed, might detect it as a gamma-ray burst or a strange transitory beacon. They would record the death of a planet, a warning etched in light across the cosmos. But as those shockwaves fade into the greater silence of space, what remains of Earth is not a planet, but the ghost of one. The once familiar blue planet, wrapped in oceans and clouds, is now reduced to a molten sphere surrounded by a haze of glowing gases and radioactive dust. The atmosphere, that delicate veil that nurtured every breath of life, would linger only for a moment in the wake of such annihilation. The surviving fragments of gas and vapor would either be ripped away entirely or twisted into something monstrous. A churning, radioactive storm of death, swirling above a scorched to airless wasteland. In the first few minutes after the impact, whatever portion of the atmosphere survived the direct blast would be in complete disarray. Ionized gases, stripped of electrons by the flood of radiation, would spiral violently around the planet in chaotic magnetic loops. These gases would not behave like air anymore, they would move like plasma, glowing faintly as they emitted radiation. The heat still radiating from the molten surface would continue to push this material outward, creating a luminous shroud around the planet, a brief, terrible imitation of an aurora. It would be beautiful from afar, a swirling halo of light and color, but up close it would be lethal beyond measure, suffused with gamma rays, X-rays, and high-energy particles. In this new and hellish environment, chemical reactions would no longer follow the rules of normal physics. The oxygen that once fed fire and breath would have long since bonded with metals and silicates, locked into molten rock or vaporized into space. Nitrogen, once the stable backbone of Earth's air, would become ionized and unstable, fusing into exotic compounds under the influence of extreme heat and radiation. The atmosphere would become a toxic soup of radioactive isotopes, cesium, iodine, strontium, uranium dust, each glowing faintly as it decayed. These would form temporary clouds of fallout, drifting across the molten surface in slow, ghostly movements before dissipating into the void.
If any remnants of gases clung to gravity's grasp, they would circle the planet in enormous glowing vortices, radioactive storms, spinning and colliding in the upper layers of the decaying atmosphere. But these storms would not resemble hurricanes or weather systems as we know them. They would be silent and deadly, their winds made of plasma instead of air. Their lightning bolts composed of radiation bursts that could split atoms apart. Magnetic fields twisted by the immense energies of the blast would steer these storms like invisible shepherds, forcing them into violent spirals that would gradually consume what little atmosphere remained. The heat from the molten surface would ensure that any attempt by gases to cool and condense would fail. Raindrops could never form again. Any moisture that tried to gather would instantly vaporize, feeding the relentless updrafts of radioactive gas. The few surviving molecules of carbon dioxide or water vapor would either be broken apart by radiation or ejected into space by sheer kinetic force. The result would be an irreversible loss, the planet's atmosphere bleeding away into the vacuum, molecule by molecule, until there was nothing left to hold. In time, perhaps within hours or days, the gravitational pull of what remained of Earth would no longer be enough to keep its atmosphere bound. The continuous radiation and thermal pressure would push the remaining gases outward in expanding waves. A planetary wind would form, a last exhalation from a dying world, sending the final traces of air into space as a thin, glowing mist. Eventually, that mist would disperse entirely, leaving behind an airless, silent world,
its surface hardening slowly as the molten rock cooled over centuries. The transition from atmosphere to void would mark one of the most haunting phases of the planet's destruction. Without the insulating blanket of air, the exposed surface would cool unevenly, one side facing the sun and remaining blisteringly hot, the other freezing into brittle glass under starlight. The difference in temperature would cause the newly formed crust to crack and fracture endlessly, producing plumes of gas and molten debris that briefly rise before being sucked into the vacuum. The planet would look as though it were still breathing, faint jets of light and vapor erupting from its surface. But these would be its last mechanical spasms, not signs of life. The lingering radioactive dust and plasma surrounding the planet would slowly drift outward, forming a thin, shimmering ring around the dead world. To a distant observer, this ring might look almost like Saturn's, but instead of ice and rock, it would consist of glowing ash and metallic vapor, the pulverized remains of continents and atmosphere. Over time, solar radiation from the sun would push these particles farther out, dispersing them into interplanetary space, leaving behind only traces of the catastrophe that once was. Without an atmosphere, Earth's surface would be utterly unrecognizable. The once blue oceans would have become black, glassy basins, frozen solid and fused with rock. The mountains and valleys would be gone, replaced by vast plains of cooled magma. The absence of air would mean no sound, no wind, no erosion, only silence and stillness. The landscape would be bathed in hard, unfiltered sunlight by day and total darkness by night, unprotected from cosmic rays and meteoroids. The concept of weather, of seasons, of life itself would vanish completely. The radiation left behind by the blast would linger for thousands of years, saturating the crust and poisoning any chance of recovery. Even if, by some cosmic accident, conditions stabilized enough for gases to slowly reaccumulate, the planet's magnetic field, disrupted and likely destroyed during the earlier stages, would no longer protect it. Any new atmosphere would be stripped away by solar wind before it could form. Earth would remain a scorched, airless relic, a warning to any who might look upon it from afar. And yet this aftermath is only the planetary scale of the destruction. The forces unleashed would not be confined to the atmosphere or the crust. The unimaginable compression of energy, the bending of spacetime, and the breaking of physical limits could trigger something far greater, a chain reaction that spreads beyond the boundaries of Earth itself. The destabilization of spacetime in one place might not stop there. The very laws of physics, stretched beyond their limits, could begin to unravel locally, a ripple effect that spreads outward into the solar system, threatening to consume everything caught within its expanding distortion. When an event of such unimaginable magnitude unfolds, one that compresses near infinite energy into a single point, shatters a planet and bends the fabric of reality itself, it does not simply end with silence. The universe is not a passive stage upon which destruction plays out. It is a living dynamic fabric of spacetime that reacts to the forces within it. And when that fabric is torn, it can ripple outward like a wound that refuses to heal. This is where the catastrophe escalates beyond a planetary tragedy, into a cosmic chain reaction, as the distortion of spacetime itself begins to spread through the solar system. At the moment Earth's annihilation reaches its peak, the density of energy becomes so extreme that the very geometry of spacetime starts to warp. Normally, Einstein's general theory of relativity ensures that gravity and energy interact in predictable ways. Massive objects curve space, and space tells objects how to move. But this explosion, this uncontrolled release of relativistic energy would push the laws of physics into a realm they were never meant to handle. Space would begin to fold and stretch erratically, not as a smooth wave like a normal gravitational ripple, but as a chaotic distortion where time, energy, and motion lose coherence. At first, these distortions would resemble gravitational waves, expanding ripples radiating outward from the destruction site. But the magnitude would far exceed anything ever produced naturally, even by colliding neutron stars or black holes. The amplitude of the waves would be colossal, twisting the geometry of the solar system as they expanded.
Space itself would begin to oscillate, causing planetary orbits to fluctuate unpredictably. For brief moments, the distances between celestial bodies would change, not because the planets moved, but because the very space between them warped.
These distortions would not remain uniform. Some regions of space might stretch, others compress. The result would be regions where time slowed to a crawl, while nearby zones accelerated unnaturally. The balance of gravitational fields around the Sun, which holds every planet in its orbital harmony, would be disrupted. The invisible web of motion and mass that keeps the solar system stable would twist into knots. Mercury might spiral inward, Venus could be nudged into a new orbit, and the outer planets might feel a subtle but relentless tug drawing them closer to the chaos. As the space-time ripples propagated outward, they could begin to interact with themselves, overlapping, interfering, and amplifying. In quantum physics, energy fields can combine to produce resonance effects, where one wave amplifies another. Here, those resonances would occur on a cosmic scale. Where two or more distortions intersect, the curvature of space could intensify dramatically, forming localized singularities, miniature tears in the fabric of reality. These singularities might briefly behave like black holes, consuming whatever matter or radiation passed near them before collapsing or merging. In effect, the destruction of Earth could seed the solar system with temporary unstable gravitational anomalies. The Sun itself would feel the effects next. As space-time distortions reached its core, the delicate balance of fusion and pressure that defines its stability could be slightly perturbed. Even a minor alteration in the Sun's internal equilibrium might change its energy output, leading to temporary surges or fluctuations in solar radiation. The surface could experience massive flares, launching walls of plasma millions of kilometers high. For distant observers, the solar system would appear as if its star were spasming, flickering erratically as it responded to the space-time trauma spreading through its domain. In the outer solar system, the giant planets, Jupiter, Saturn, Uranus, and Neptune, would react in their own ways. Their immense masses might partially absorb or deflect some of the gravitational chaos, creating new waves that bounce back toward the center. These secondary ripples could interfere with the primary distortions, creating a pattern of chaotic oscillations throughout the region. The orbits of moons, asteroids, and comets would become unstable. Entire systems of satellites could be thrown from their paths, spiraling into their parent planets or cast into interstellar space. And then there is the possibility, however theoretical, that the distortions could reach a critical threshold. Energy and curvature feed on each other. The more space bends, the more energy is concentrated, and the more energy, the more bending occurs. In extreme cases, this feedback loop could cause space-time to collapse locally, forming a cascading chain of micro-singularities. These would not behave like stable black holes, but rather as transient voids, tears in the continuum that expand briefly before evaporating in bursts of radiation. Each micro-collapse would generate another pulse, sending yet more gravitational and electromagnetic waves into the system. The cumulative effect would be chaos on a solar scale. The planets, moons, and remnants of Earth would find themselves within a turbulent sea of distorted spacetime, where the rules of physics begin to fluctuate. The constants of nature, the speed of light, the strength of gravity, the charge of particles, could vary locally for fractions of a second. The atomic structure of matter might begin to unravel where these distortions are strongest, as the stability of quantum fields falter. Even light itself could become trapped or redirected in unpredictable ways, creating bizarre mirages and flashes as it encounters warped regions. From a distance, this event would look like the solar system convulsing, a cascade of invisible waves rippling outward, bending light, shifting gravity, and altering motion. For nearby systems, it would appear as a flickering beacon, a gravitational and electromagnetic anomaly spreading through the void. The solar system's once stable orbits and rhythms would dissolve into chaos,
its planets locked in a slow-motion unraveling that could last for millennia. And in the heart of it all, where Earth once existed, the distortion might never fully fade. The density of energy, the gravitational trauma, and the quantum chaos could combine into something far worse than a simple void. The atoms of what once was Earth might be ripped apart at a fundamental level, their quantum fields overwhelmed by the runaway reaction of space-time itself. This is where the chain reaction would reach its ultimate endgame, not just the destruction of a planet or the warping of orbits, but the total disintegration of matter, as the physical laws governing existence begin to fail within that region of space. The solar system would not just be destabilized, it could become the epicenter of a growing tear in reality, a wound in space-time that devours itself from within. When energy reaches a level that is so extreme that it no longer just destroys matter, but unravels it, the universe enters a realm beyond comprehension. This is where the story of Earth's annihilation stops being about heat, fire, and shockwaves and becomes about the death of matter itself. The final act is one of total disintegration, where atoms, the very building blocks of everything that has ever existed, are ripped apart as their quantum fields are overwhelmed by an impossible influx of energy. At the most fundamental level, everything we know, planets, stars, air, life, are made of fields, not solid particles. Atoms only exist because these quantum fields are stable, delicately balanced by the rules of nature. But when a near light-speed object collides with Earth and floods the surrounding region with more energy than the laws of physics can comfortably handle, that balance collapses. The familiar forces that bind the nucleus together, that keep electrons orbiting, that hold protons and neutrons in harmony, all of it begins to unravel under the weight of so much energy compressed into such a small space. At first, the atoms would ionize, their electrons stripped away in an instant by the sheer power of the radiation. The air, the oceans, and the rock would turn into a sea of charged plasma. But as the energy continues to build, it pushes past the ionization point, beyond plasma, beyond any normal state of matter. Protons and neutrons, usually bound tightly within the heart of the atom, would be torn apart by the unstoppable tidal forces of energy density. The strong nuclear force, the most powerful of all known interactions, would be overwhelmed. Quarks, the tiny subcomponents of protons and neutrons, would be released, forming a chaotic soup of unbound particles known as quark-gluon plasma. This is the same state of matter that existed microseconds after the Big Bang, raw, unstructured, and unimaginably hot.
But this wouldn't be a stable version of that primordial plasma. The energies involved here wouldn't come from a controlled expansion, as they did in the early universe. They would come from compression, destruction, and gravitational collapse, forces that drive systems toward instability. The quark-gluon soup would boil and surge in violent patterns, emitting bursts of high-energy photons and neutrinos. The boundaries between particles would blur as energy and mass become indistinguishable. Einstein's famous equivalence of mass and energy, normally a tidy equation, would turn chaotic here, with matter ceasing to exist as a defined entity. Everything that was once Earth would become a storm of pure energy, cascading outward in waves of radiation. Quantum mechanics tells us that even empty space is not truly empty. It's filled with energy fields that constantly fluctuate. But when an event like this floods a region with such overwhelming power, those quantum fluctuations themselves can become destabilized. The vacuum, the ground state of space-time, can begin to distort. It's as if reality itself starts to tear at the seams. The structure that separates one quantum field from another begins to blur, allowing particles and antiparticles to appear and annihilate uncontrollably. Virtual particles, normally ephemeral, appearing and vanishing in an instant, could begin to emerge in mass, converting the region into a chaotic quantum storm. At this point, matter doesn't just disintegrate. It ceases to mean anything at all.
The concepts of solid, liquid, or gas vanish entirely. Even the idea of temperature becomes meaningless, since temperature depends on the collective motion of particles, and there are no longer coherent particles to measure. The energy density becomes so high that space and time themselves begin to lose definition. In this zone, every quantum field is pushed beyond its threshold, forced into excitation levels so extreme that they no longer interact in predictable ways. Photons, normally carriers of light, could collide with enough energy to create new particles, which immediately collapse back into radiation, feeding an endless cycle of creation and destruction. For a brief, terrible instant, the entire mass of Earth becomes something like a localized Big Bang, a knot of energy where normal physical laws have broken down completely. Gravity, electromagnetism, the strong and weak nuclear forces, all the fundamental interactions that govern reality become indistinguishable. The quantum foam at the heart of space-time starts to froth violently, each fluctuation magnified by the torrent of energy flowing through it. Matter, space, and time blur into one continuous storm of existence, a point of infinite density and infinite chaos. From the outside, this would appear as an expanding bubble of annihilation. The light emitted would be beyond any visible color, a flood of gamma rays and exotic radiation sweeping across the void. The surrounding space would shimmer with distortions as gravity buckles under the strain, bending light into impossible patterns. Even distant observers, if they could exist, would see the event as a brief, blinding flash, followed by a spreading shadow where the planet once was. Inside that expanding sphere of disintegration, every molecule, every atom, every quantum of matter that once made up Earth would have been converted into energy and radiation. The sheer intensity of this process could trigger secondary effects in the nearby vacuum of space. The influx of energy might create pockets of instability where quantum fields fluctuate violently, briefly producing particle-antiparticle pairs that annihilate in flashes of light. In theory, this could even lead to localized vacuum decay, a phenomenon in which the fabric of space-time transitions to a lower energy state, effectively rewriting the rules of physics in that region. If that were to happen, it wouldn't just destroy the remnants of Earth. It could spread outward at the speed of light, consuming the solar system, perhaps even beyond. But even without such extreme theoretical outcomes, the total disintegration of matter would leave behind something profoundly alien. The debris from the annihilation would no longer be matter in any recognizable form, just radiation, exotic particles, and warped spacetime. Gravity would begin to draw this chaos inward, compressing the glowing remnants toward a single point. The energy, no longer able to escape its own pool, would collapse into a region of infinite density and zero volume, the birth of a black hole. This would be the final consequence of trying to reach or exceed the speed of light near Earth. The overwhelming influx of energy that began as motion would end as collapse, not only tearing matter apart, but creating a singularity that traps even light itself. And from that singularity, the story of Earth would not end quietly. The gravitational power of its birth would twist everything around it, space, time, light, into a whirlpool of destruction, marking the final chapter of a planet that once shone with life. In the aftermath of total disintegration, when matter has been stripped of its identity, when energy itself has grown too dense to escape its own gravity, the inevitable consequence is collapse. What begins as the violent release of unimaginable power ends as an implosion, a convergence of energy so extreme that it tears through the final boundaries of physics. This is where the destruction of Earth transcends into something even more catastrophic and permanent, the birth of a black hole. At first, the process would not look like a calm collapse. It would be chaotic, violent, and incomprehensible. The residual energy from Earth's annihilation, radiation, plasma, gravitational distortions, and raw space-time turbulence would swirl inward under the pull of its own gravity. Despite its explosive origins, the sheer mass-energy density would force everything back toward the center. It's like the universe itself was trying to contain the disaster by folding it in on itself. Within milliseconds, the remaining energy would become so compact that its escape velocity, the speed required to flee its gravity, would exceed the speed of light. Once that threshold is crossed, nothing, not even light itself, could get out. This moment marks the creation of an event horizon, the invisible boundary that separates the knowable universe from the unknowable. Everything that crosses it, energy, radiation, information, is lost forever from our observable reality. From the outside, this newborn black hole would appear deceptively small. Despite containing all the mass energy that once made up Earth, its diameter would be only a few centimeters, smaller than a marble. Yet within that tiny volume lies a density so unfathomable that even time itself would warp. The gravitational field around it would stretch the flow of time into near stasis. For an outside observer, it would seem as though the final moments of the collapse slowed to a crawl, frozen in a perpetual state of falling inward. The region surrounding this singularity would become a maelstrom of energy. As radiation and debris continued to spiral inward, they would form an accretion disk, an ultra-hot ring of material orbiting the event horizon at nearly light speed. The friction and magnetic forces within this disk would heat it to billions of degrees, causing it to emit bursts of high-energy radiation, X-rays, gamma rays, and jets of plasma shooting into space. These jets, accelerated along the black hole's magnetic axis, could extend for thousands of kilometers, piercing through the remains of the solar system like cosmic lances of destruction. In this phase, the birth of the black hole would resemble a miniature quasar, a phenomenon usually found in the hearts of galaxies. The light and energy released during this stage could briefly outshine the sun, visible across interstellar distances. For any civilization observing from afar, it would appear as if a star had been born and died in the same instant, its light flashing once across the dark expanse before fading into silence. The gravitational influence of this new black hole would not be confined to what remained of Earth. Even with a mass equivalent to that of the former planet, its density would allow it to affect nearby celestial bodies with alarming precision. The Moon, once orbiting peacefully, would find itself drawn inward. Its orbit would decay, tightening over weeks or months until it spiraled into the black hole, shredded into plasma and swallowed whole. The energy released from that consumption would be enough to send ripples through space-time, gravitational waves radiating outward like silent thunder. The Sun, though far larger and more massive, would not be immune to the effects. The gravitational equilibrium of the solar system would be broken. The newly formed black hole, though tiny, would act like a pebble dropped into a delicate cosmic machine, throwing everything out of balance. Planets would drift from their orbits, asteroids would veer unpredictably, and the entire system would begin to subtly shift over astronomical timescales. The destruction of one world would echo outward as gravitational instability rippled through the rest. But the true horror of this event lies not in the visible destruction, it's in what happens inside, beyond the event horizon, within that infinitesimal point of infinite density known as the singularity. All the known laws of physics break down. Matter ceases to have form. Space and time themselves stop behaving as we understand them. Every coordinate of distance collapses into one, every tick of time into eternity. What once was Earth, its mountains, its oceans, its cities, its memories, would be reduced to pure information, encrypted into the curvature of space-time and sealed forever within the black hole's event horizon. Some physicists suggest that information is never truly lost, that it remains encoded on the surface of the event horizon itself in microscopic fluctuations known as the holographic principle. If that's true, then the entire history of Earth might still exist, not as a world, but as a pattern of information woven into the boundary of the black hole.
Every human life, every sound, every story would persist as ghostly imprints on the edge of eternity, preserved but forever unreachable. Over time, as the black hole radiates away energy through Hawking radiation, it would slowly evaporate. For a black hole of Earth's mass, this process would take far longer than the current age of the universe, an inconceivably slow fading of existence. Yet even this end is not peaceful. As the black hole loses mass, it becomes smaller and hotter, accelerating its decay until it finally releases all its stored energy in a single burst. When that moment comes, billions or trillions of years in the future, the last trace of Earth would vanish in a flash of pure radiation, a final whisper in the cosmic dark. The irony is profound. An attempt to move at or beyond the speed of light to reach the frontier of physics would not only destroy a planet, but give birth to one of the universe's most mysterious entities, a singularity, a cosmic tombstone marking where a world once existed. It would be both the ultimate end and the ultimate transformation. Matter turned to energy, energy turned to gravity, and gravity turned into the infinite silence of a black hole. And even after that silence spreads, the story doesn't quite end. For the black hole's gravitational waves, its radiation, its lingering distortions in spacetime would ripple outward, reaching distant planets, distant stars, and perhaps even other civilizations. To them, the brief, brilliant pulse marking Earth's death would be a cosmic warning, a reminder that tampering with the boundaries of light and motion is not merely dangerous, but existential. But the destruction would not stop there. From that singularity, fragments of energy, matter, and radiation could be ejected into the void, debris moving at near light speed, carrying with them the final fury of Earth's end. These remnants, though small, could bring devastation wherever they go, turning the black hole's birth into the spark of a wider cosmic calamity. The birth of a black hole is never a clean event. It is not the quiet swallowing of matter into an invisible point. It is chaos incarnate, a storm of energy and gravity that tears at the seams of the universe. When Earth collapses into a singularity, the process would not simply consume everything nicely. Tremendous quantities of energy would erupt outward before the final collapse, flinging debris, the last fragments of the planet's existence, across the solar system at velocities so high that they would blur the line between matter and light itself. These would be the light-speed debris, shards of destruction hurled outward with apocalyptic energy, each one carrying the power to devastate worlds.
In those first seconds after the collapse, the gravitational and electromagnetic forces would be in violent competition. As the event horizon forms and matter spirals inward, immense magnetic fields would twist and snap, releasing colossal bursts of radiation and accelerating nearby particles to relativistic speeds, that is, to fractions of the speed of light. Chunks of molten rock, vaporized metals, plasma, and atomic nuclei would be caught in these fields, flung outward in narrow jets extending for millions of kilometers. These jets would not be slow, fiery trails like volcanic eruptions or supernova flares. They would be cosmic lances, columns of incandescent death traveling so fast that even the space around them would glow from their passage. Each fragment, no matter how small, would carry unthinkable kinetic energy. A piece of debris no larger than a grain of sand, moving at near light speed, would strike with the force of a thermonuclear bomb. A rock the size of a car would hit with enough power to vaporize a moon. And if larger fragments, say chunks the size of mountains or continents, were ejected, their energy release upon impact would be beyond calculation. The energy of their collisions would equal or exceed that of the very explosion that destroyed Earth in the first place. These fragments would become projectiles of annihilation, racing outward in every direction. Some would be captured by the sun's gravity, drawn into elongated orbits that eventually bring them crashing into the inner planets. Mercury, closest to the chaos, would likely be the first to feel the wrath.
A single relativistic impact could strip half its crust, sending molten materials spraying into space. The once airless, silent world would momentarily blaze with light, its surface reshaped by energies more violent than anything since the solar system's formation. Venus, with its dense atmosphere, would fare even worse. As debris slammed into its upper layers, the collisions would unleash bursts of radiation and shock waves powerful enough to ignite its carbon dioxide-rich air. The planet's already hellish surface would be scorched anew, its clouds turned into glowing plasma. For a brief time, Venus could appear brighter than the sun itself, a shining scar of destruction visible across the solar system. And then there's Mars, the quiet, cold, red planet that once inspired dreams of human colonization. The light-speed debris from Earth's demise could arrive there minutes or hours later, depending on their trajectories. When they hit, the impacts would excavate craters hundreds of kilometers wide, melting ice caps, shattering the crust, and possibly altering the planet's orbit. Any trace of its fragile atmosphere would be stripped away completely, and its surface would be blasted into glowing dust. Mars, once thought of as a future refuge for humanity, would become another casualty of the catastrophe, its fate sealed by the echo of Earth's final moment. The debris wouldn't stop there. Many of the fragments, unbound by any planetary gravity, would continue outward toward the outer planets. Jupiter and Saturn, with their massive gravitational fields, would act as giant nets, capturing countless high-speed fragments. But instead of saving the solar system, this would only amplify the chaos. As the debris slammed into their thick atmospheres, the kinetic energy would ignite unimaginable explosions, massive firestorms and shock waves that would send visible ripples through their cloud bands. Jupiter's great red spot, already a storm larger than Earth, would be dwarfed by these new tempests, fueled by the infusion of alien matter traveling near light speed. Saturn's rings, those delicate icy bands that have encircled the planet for billions of years, would not survive. Light-speed debris would shred them instantly, vaporizing ice particles and scattering the remains into space. The debris could even punch through Saturn's upper atmosphere, creating luminous scars of destruction visible from interplanetary distances. Each impact would send waves of electromagnetic energy coursing through the solar wind, like the echoes of Earth's death resonating across the void. Beyond the gas giants, fragments would continue to race toward Uranus, Neptune, and the Kuiper Belt, a vast region filled with frozen bodies and ancient relics of the solar system's formation. These distant worlds, long untouched by significant violence, would be awakened by the arrival of the high-velocity storm. Ice would vaporize instantly, small moons would shatter into dust, and countless comets would be knocked from their orbits, sent hurtling toward the inner solar system. In a grim irony, Earth's destruction could unleash a secondary apocalypse years or centuries later, a barrage of redirected asteroids and comets raining down on whatever worlds remained. And what of the fragments that escape entirely? Many would accelerate beyond the pull of the sun, racing outward into interstellar space. Each one would become a wandering harbinger of destruction, a fragment of Earth turned into a weapon. Traveling at a significant fraction of the speed of light, these shards could journey for millions of years, crossing vast distances between stars. If they ever collided with another planetary system, the impact would be cataclysmic, a burst of energy so immense it could sterilize entire worlds in an instant. To distant civilizations, such impacts might appear as sudden, inexplicable flares, mysterious flashes in the darkness, not realizing that they were witnessing the aftershocks of a world long gone. In the near aftermath, the solar system would be transformed into a debris field of unimaginable violence. Space itself would glitter faintly with particles of vaporized rock and metal glowing as they absorbed radiation from the sun. The inner planets would be scorched ruins, their surfaces cratered and boiling. The outer planets would bear storm scars for millennia. Even the delicate balance of the solar system's gravitational harmony could begin to shift as the redistribution of mass and energy alters orbital dynamics. Over eons, the system might settle into a new equilibrium, colder, emptier, and haunted by the traces of what once was. From a cosmic perspective, These fragments of light-speed debris would be the last testament to Earth's existence. They would carry within them the isotopic fingerprints of the planet's crust, its metals, its oceans, even traces of what once were living things, now fused into plasma and atomic fragments. In a distant future, when these shards finally slow or collide with another object, they might deposit the faintest dusting of those elements, the ashes of Earth, onto alien worlds. In that sense, even in destruction, Earth would not vanish entirely. It would scatter itself across the cosmos, its remains becoming part of new systems, new stars, perhaps even new life someday.
Yet for now, in this vision of cosmic ruin, those lightspeed fragments would be symbols of unrestrained power. The echoes of a mistake too great to undo. The attempt to conquer the speed of light would have turned an entire planet into a weapon of mass extinction, sending the last remnants of humanity's home on a one-way journey through eternity. And though the violence would eventually fade, the memory of that explosion, the flash of impossible light, the storm of relativistic debris, would be etched into the universe forever. But even that haunting aftermath, catastrophic as it seems, would not be the end. Because when so much energy is released in such a small region, the entire event would blaze across the heavens, visible from other star systems and even distant galaxies, a brilliant, vanishing beacon announcing Earth's final moment to the cosmos. Across the infinite dark of space, light is the storyteller of the cosmos. It carries the whispers of birth and death, of stars forming and galaxies colliding, of the ancient fire from the dawn of time. Every supernova, every quasar, every explosion ever to tear through the void has left behind a luminous fingerprint, a signal for anyone watching to interpret. When Earth finally meets its end through the unimaginable violence of light-speed destruction, the universe itself would bear witness. The planet's final act would not pass quietly into darkness. It would blaze across the heavens as a brief, blinding burst of cosmic light, visible across galaxies, marking the moment when an entire world was erased. From the instant the light-speed object collides, the release of energy would be beyond anything humanity has ever conceived. Trillions upon trillions of joules unleashed in a fraction of a second, not just in one spectrum, but across them all. Gamma rays, X-rays, ultraviolet light, visible radiation, and radio waves would erupt together, forming a pulse so intense that it would outshine the sun by billions of times. In that instant, the night sky, even from light years away, would flare with the brilliance of destruction. To an observer in another star system, the flash would appear as a sudden, piercing point of light, briefly brighter than any other star in the sky, before fading into nothingness. At cosmic scales, time behaves differently. Light takes years, even millennia, to travel between stars. This means that for countless civilizations scattered across the Milky Way, the story of Earth's end would arrive not as an immediate event, but as a message from the past. 1,000 years from now, perhaps, some distant astronomers orbiting an alien sun might notice an anomaly, a sudden gamma-ray burst emanating from the coordinates once known as Sol. Their telescopes would register the data. The spectrum would be unlike any known supernova, shorter-lived yet unimaginably bright. It would carry the energetic signature of matter torn apart at near light speeds, of space-time itself convulsing under impossible stress. They might debate what it was, a failed experiment, a collapsed planet, the death of an artificial world, never knowing they were witnessing the echo of humanity's greatest mistake. In the seconds following the collision, the energy would radiate outward in every direction. The gamma-ray burst alone, the most energetic form of light, could extend for light years, carrying with it enough power to sterilize any nearby worlds. The pulse would be brief, lasting perhaps only a few seconds or minutes, but in that time, it would shine brighter than the combined output of billions of stars. Space-based observatories across the galaxy, if they existed, would detect the burst instantly. It would register as one of the most intense events in the known universe, rivaling the cataclysms of dying stars and colliding black holes. Closer to home, the effects would be catastrophic on an interplanetary scale. The light itself would carry enough radiation to scorch neighboring worlds.
The moon would be bathed in lethal gamma rays, its surface temperature spiking for a brief instant before cooling into silence. Mars, already reeling from the earlier debris impacts, would be swept by the radiation front, its thin atmosphere stripped away completely. Even the gas giants, far out in their orbits, would feel the touch of the light, their cloud tops briefly fluorescing with exotic reactions as high-energy particles bombard their atmospheres.
But from beyond the solar system, from across the Milky Way, the event would look eerily beautiful. The light from the explosion would spread outward as an expanding sphere, glowing in multiple wavelengths. At visible frequencies, it might appear as a sudden blue-white flare, fading within hours or days. In the infrared, the afterglow could linger for weeks as the remaining dust and plasma cools. For distant galaxies, this flare would be so bright that it might momentarily rival the combined light of entire star clusters. It would be recorded as a cosmic transient, a mysterious flash with no known precursor, an anomaly to be cataloged, studied, and puzzled over for eons. The event would also send out a flood of gravitational waves, ripples in the fabric of space-time itself. These waves, invisible but powerful, would spread outward along with the light, distorting space ever so slightly as they pass through distant stars and planets. To an advanced civilization with sensitive instruments, the signature of these waves would reveal the truth that a massive body had been destroyed by an event at the limits of physical possibility. They would see the rhythm of space-time itself wobble, matching the brief pulse of light that accompanied it, a cosmic heartbeat marking the moment Earth ceased to exist. And what would remain after that flash fades? From billions of kilometers away, the region once occupied by Earth would go dark. There would be no lingering glow, no visible debris field reflecting sunlight. The black hole that formed in the aftermath would be invisible, detectable only through its gravitational influence. Over time, the light from the explosion would continue to travel outward, crossing interstellar distances, eventually leaving the Milky Way entirely. Long after the last human name was forgotten, long after the sun itself burned out, Earth's final light would still be moving, a silent, radiant ghost traveling through the dark, carrying with it the memory of everything that ever was. For astronomers in distant galaxies, perhaps millions of years in the future, that faint photon storm might be the only evidence that our world ever existed. It would arrive as an ancient echo, long after the civilizations that caused it had vanished. They might capture the light and analyze it, finding strange chemical fingerprints, traces of oxygen, carbon, silicon, and iron. The spectral remnants of oceans, continents, and perhaps even life. They would never know that what they were studying was once a living planet, one that dreamed, built, and reached too far. This blinding burst would become a cosmic tombstone, a flash of brilliance lasting only a moment compared to the age of the universe, yet visible across unimaginable distances. It would symbolize both the heights of human ambition and the depths of its hubris. A warning written not in words, but in light, echoing endlessly through the dark fabric of creation. Even billions of years later, when the light from the explosion fades into the cosmic background, the gravitational ripples would persist, subtle distortions in space-time that might never fully disappear. The universe itself would remember what happened here, in the way it subtly curves, in the way it silently holds the scars of that impossible event. But for those who were there, if there could even still exist in a meaningful sense, the end would not appear as a grand cosmic display. For them, time would nearly stop as the speed of light was approached.
everything around them would stretch, distort, and freeze in an eerie stillness before vanishing in an instant. The universe beyond would collapse into a single, blinding flash, a final moment of perception before all of reality itself was consumed by the light they had unleashed. From the human point of view, the end of everything would not come as an explosion or even as chaos. It would come as silence. To those caught within or near an object accelerating toward the speed of light, time itself would begin to unravel long before the universe around them was destroyed. This final human perspective, the view from the edge of the impossible, is perhaps the most haunting part of the entire scenario. Because from the inside, the destruction of Earth wouldn't look like a fiery cataclysm or a flash of cosmic light. It would feel like eternity frozen into a single moment, where time, motion, and existence collapse together before vanishing entirely. As velocity approaches the speed of light, relativity begins to play its most profound trick: time dilation. To an outside observer, anyone traveling at near light speeds would seem to move more and more slowly, as if caught in slow motion. But from the traveler's own perspective, time inside the ship or within their own consciousness would feel perfectly normal. The rest of the universe, however, would appear to accelerate uncontrollably. Seconds would stretch into years, minutes into millennia. Distant stars would rush together into a single point of unbearable brightness ahead, while behind them, space would fade into infinite darkness. Now imagine this from the point of view of someone or something that has somehow reached or exceeded light speed near Earth. For them, the moment of acceleration would not feel violent at first. It would feel like stillness. As the ship or body closes in on the ultimate limit, every external frame of reference, every tick of time, every flash of light, every vibration of matter would slow down until it almost stopped. The world around them would begin to distort, flattening in the direction of motion. Colors would shift to extremes, reds fading into infrared, blues into ultraviolet, until the visible spectrum itself disappears. The universe would seem to compress into a tunnel of white radiance ahead, an infinitely bright horizon where all of space and time converge.
From this vantage point, the destruction of Earth would unfold not as an explosion, but as an eternity frozen mid-motion. The traveler, existing within their own subjective timeline, would see the planet below stretch and warp, light from its surface bending and folding around their field of vision. In one direction, they might glimpse the final moments of the world, oceans igniting, continents shattering, all stretched into an infinite instant. In the other, they would see only darkness, the afterimage of what used to be. Their perception would cease to function in the way we understand it. Every photon, every sound, every second would arrive at once, a single, incomprehensible flood of reality, compressed into a fraction of awareness. To them, it would feel as though time had stopped. The heart might beat once, maybe not even that. Thoughts would hang suspended, unfinished. The idea of motion would vanish completely, because at light speed, space and time lose their separation. The traveler would not move through the universe anymore. They would become part of it, stretched across it, fused into the very fabric of space-time. Every location along their path would collapse into the same instant, every moment into the same point. There would be no before or after. There would only be now, an infinite, eternal now. Meanwhile, from the outside, for any observer left to witness the event, even briefly, things would appear altogether different. They would see the accelerating object slow down as it approached light speed, frozen in time, glowing ever brighter but never quite reaching its destination. Then, in an instant beyond perception, it would vanish. The light from its surface would be red-shifted into oblivion, disappearing from view. To them, the traveler would seem to fade into nothingness, swallowed by their own velocity. There would be no explosion, no sound,
just absence. If there were people still alive on Earth in those final milliseconds, their experience would be radically different, but equally surreal. They would never truly see the end. The collision or release of energy would happen faster than their brains could register it. One instant, they would be looking at the sky, seeing a strange, bright streak. The next, reality itself would end. The atmosphere would ignite faster than light could carry the image of its destruction to their eyes. Their entire sensory experience, light, sound, touch, thought, would be wiped out before it could even be processed. From their perspective, the universe would simply blink out as if someone had switched off existence. In those final fractions of a nanosecond, the human experience would break down at every level. Nerve signals, limited by the speed of electrical impulses, wouldn't have time to travel from the senses to the brain. Neurons would never complete their final firings. The physical structure of the body would disintegrate faster than the mind could perceive it happening. To the individual, there would be no pain, no awareness of death, only a sudden and complete cessation of being. In essence, the end of the world would come not as horror or suffering, but as instantaneous oblivion. But if consciousness could somehow persist in that instant, if awareness could stretch just a heartbeat longer than matter itself, what would it perceive? Perhaps it would see the collapsing of time as an infinite panorama, every moment of life flashing not as memory, but as reality itself. The past, present, and future would merge. The faces of loved ones, the sound of the wind, the feel of sunlight, everything that ever was and ever could be might appear together, not in sequence, but as one eternal moment. That final perception might feel like a kind of transcendence, the human mind brushing against the infinite just as the universe takes it away. Outside of that subjective experience, time would continue, at least for the cosmos. To distant observers, the destruction would have already happened long ago, the light of it racing outward into the void. But for those caught within it, the last instant would last forever. The closer one moves to light speed, the slower time passes relative to the universe. So for anyone at or beyond that threshold, the final moment of existence could stretch indefinitely. The world would remain frozen in that instant of annihilation, never quite finishing its destruction from their perspective. They would exist eternally in the moment before the end, unaware that the rest of the universe had already moved on. It is a paradox beyond human comprehension. From one frame of reference, Earth is destroyed in a blinding instant. From another, it never finishes dying at all. To the traveler, the explosion would appear motionless, eternal. To the universe, it would be over before it began. This collapse of perception, of cause and effect, is what makes the idea of light-speed travel so haunting. It doesn't just threaten to destroy matter, it threatens to destroy meaning itself. And so, if anyone or anything were conscious in that final breath before the speed of light is breached, their last experience would not be of fire or pain or chaos. It would be of time stopping, of the universe holding its breath, a single, frozen instant stretching into infinity, then nothing. Yet the universe would remember what they could not. Long after that moment ends, long after human awareness dissolves, the light of that destruction would still travel outward, carrying the story of their final instant to the stars. It would whisper across the cosmos that once there was a world here, a world that dreamed of touching light and paid the ultimate price for trying. In the end, the lesson is as chilling as it is profound. Traveling at the speed of light is not simply a technological challenge waiting to be solved. It is a line drawn into the very structure of reality itself. It is the ultimate boundary woven into the laws that govern energy, matter, and existence. To cross that line is not merely to go faster, but to unmake the very foundations that hold the universe together. For all of humanity's dreams of faster-than-light travel, of warping through the stars or racing alongside photons, the truth remains brutally simple. If such a thing were ever to happen near Earth, it would not just break physics. It would erase the planet entirely. Everything that has come before, the energy buildup, the shockwaves, the gravitational distortions, the annihilation of atmosphere, the disintegration of matter, all of it points to one undeniable truth. The speed of light is not a threshold meant to be crossed. It is a cosmic safeguard, an immutable limit written into spacetime to prevent creation itself from unraveling. When Einstein first formulated relativity, he revealed more than an equation. He uncovered the architecture of reality. To accelerate mass to the speed of light would require infinite energy, and infinity, in the physical world, is synonymous with destruction.
If any object, no matter how small, somehow reached or exceeded that speed near our planet, the result would not be a triumph of science or exploration. It would be annihilation on a scale beyond comprehension. The very act of approaching light speed would cause an exponential surge of energy, turning the object into a weapon of cosmic proportion. Before it even reached full velocity, its interaction with space, air, and matter would unleash enough power to vaporize continents and boil oceans. And once that threshold was breached, the consequences would no longer be confined to Earth. The cascade of energy, space-time distortion, and gravitational collapse could ripple outward through the solar system, destabilizing orbits, disintegrating planets, and perhaps even tearing a scar through the very fabric of the cosmos. There would be no explosion in the traditional sense, no single blast that could be seen and then forgotten. Instead, there would be a conversion, the transformation of matter into pure energy, the translation of everything tangible into the incomprehensible. The crust, the oceans, the atmosphere, every molecule of life and stone, all would dissolve into radiation, into waves of light and heat that would race outward forever. Earth would cease to be a world, it would become an expanding sphere of energy, a ghostly echo of its former self that fades as it spreads into infinity. And for all of this, the cause would not be malevolence or intent, just a momentary violation of a rule that has existed since the dawn of time. The speed of light is more than a number. It is a boundary between existence and chaos. Everything within the universe, from galaxies to atoms, is built upon its constancy. To surpass it would not just defy the laws of physics, it would unravel them. Space and time themselves would begin to fold, distort, and collapse. What we think of as cause and effect would dissolve. Past, present, and future would blur into one. The universe around such an event would no longer obey logic, only entropy. For humanity, the warning could not be clearer. Our curiosity, our drive to explore and understand, has always pushed us to reach further, to touch the stars, to see what lies beyond the horizon. But there are boundaries that are not meant to be crossed, not because they're dangerous in the ordinary sense, but because they are essential to reality itself. The laws of physics are not barriers designed to keep us small. They're the scaffolding that keeps the cosmos from collapsing into chaos. If lightspeed travel were somehow achieved, the dream of exploring the stars would transform into a nightmare of cosmic proportions. Every attempt to harness or control that much energy would come at a catastrophic cost. The heat, the radiation, the gravitational distortions, all would converge into an event that would leave no trace of Earth behind. Our blue planet, with its delicate balance of life and chemistry, would vanish in an instant, its story reduced to a flicker of radiation speeding through the void. And what of the rest of the universe? Even if it survived, the echoes of such an event would carry on forever. The light of Earth's destruction would travel outward at the same speed that caused it, an eternal reminder of the moment we overstepped the line. Distant civilizations, if they exist, might one day detect that burst of energy and wonder what kind of power could obliterate an entire planet so suddenly. They might see it as a warning, a cosmic scar reminding all who come after that even in a universe governed by infinite possibilities, some limits are sacred. So when we look up at the night sky and marvel at the light that has traveled across eons to reach us, we should remember what it truly represents. Each photon, each glimmering star is moving at the ultimate speed, the fastest anything can ever move without tearing reality apart. The light we see is not just beauty, it is stability, the proof that the universe knows how to hold itself together. To try and surpass that would be to challenge existence itself,
And existence, when challenged at its core, responds not with mercy, but with obliteration. In the end, the pursuit of light-speed travel near Earth wouldn't open the door to interstellar journeys or new civilizations. It would close the final chapter of our planet's history. Every life, every memory, every achievement would vanish before a single thought could finish forming. The planet that once teemed with oceans and forests, cities and dreams would become a silent, radiant echo, a pulse of light racing endlessly into the dark. The warning, then, is simple but absolute. The speed of light is not a target to be conquered, it is a limit to be respected. It is the foundation of causality, the keeper of order, the universe's way of saying, this far and no further. To break that rule would not just change the world, it would end it. And so, as humanity continues to push the boundaries of science, to reach further into space and imagination, we must remember that some frontiers are not meant to be crossed. Not because they are dangerous in the ordinary sense, but because they are essential to reality itself. If light-speed travel ever occurred near Earth, it wouldn't be a step forward, it would be the final moment before silence. Not the silence of space, but the silence of existence itself. A silence so complete that even time would bow and vanish before it. That is the true cost of breaking the ultimate law. Not glory, not progress, but erasure. The cosmos, vast and eternal, will continue long after, indifferent yet unbroken. And somewhere, carried on waves of ancient light, the memory of our world will still drift across the universe, a single, fleeting spark in the endless dark, reminding all who might see it what happens when creation dares to outrun itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.